Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look at how to debug your code. When creating applications, there will be times when your application will not do what you expect it to. This will either be because when you attempt to compile your application, the compilation fails, or the application runs, but it does something quite unexpected. We will first look at problems you can encounter when your application fails to compile. We will first attempt to set up our integrated development environment. If you go up to the Windows Options menu option and click on Compiler. There are two entries in here, one to create a log file and one for detailed results. We will click on the detailed results to get full results from our compilation. And once we have clicked OK, the next compile will pick these up. Our application at the moment has no errors. When you click on the compile icon, it will attempt to compile the application, and in this case has compiled quite cleanly. It also gives you a list of all the files it has interrogated to work out what needs to be included in your executable. We have two include files at the top of our application, the Windows 32 API and the Common Display Library. The compiler looks at these files and any files they reference, and pulls in all the code that is referenced in your application. This will mean it looks at a great many files and functions within these include files, but will only keep the ones that are directly referenced by your code. So let's look at putting in an error which will fail to compile. So we have now a for next loop within our code for the long R equals 1 to 10. However, we have not declared the long R variable. Therefore, when we attempt to compile this application, PowerBasic will tell us that there is an error at compilation time. We click on the icon and we get the error message appearing. It's telling us we're missing the declaration for long R, and it even tells us that it occurs on line 18. This is the first reference of this variable in the for next loop. So we can see quite easily from this error message where the problem has occurred and what it is we need to do to fix the problem. Adding in a reference to declare our variable locally should fix this problem quite nicely. So having got that line of code in place, we can now attempt to compile again, and the application will tell us it has compiled quite cleanly with no errors. So we have fixed a compilation error. This is probably one of the easiest type of errors you can actually pick up on. The next type of error we will look at on the compilation side is where there is a missing end of block. If we're putting a statement in to say if A equals 1, then do something. You would expect each of these if blocks to have an end if. If the end if is missing, our compilation will fail. This can be quite easy to spot if it's a single if statement. However, if you have a nested if, where there are blocks within blocks, it can sometimes be a little difficult to work out where the end ifs are. The easy way around this is to indent your code. That way, when you work back to the end of a block, you should be back at the left-hand side of the code. If we deliberately take out one of the end ifs and attempt to compile our application, we will see a failure to compile. This means that the indenting of code isn't just to make the code look pretty. It has a very practical purpose. We've now taken out the end if statement. If we attempt to compile now, the application will not compile. We're getting an error message to say a for loop is expected. It's not finding the next statement where it expects to see it. This is because we're missing the end if. Therefore, the error message says line 29, but it's not line 29 the error actually has occurred on. This can make the end of blocks somewhat difficult to track if you have a lot of blocks. However, if you see a message like this, you can probably guarantee there's a missing end statement, either in an if command or a select case command. Once you put the endif back in place, you should find the code will compile quite cleanly. But in this case, it doesn't because we have not yet declared the A or the B variables. So as we did before, we will declare them locally, and our compilation should now complete without error, which it does. Once you have your compilation errors out of the way, you can then start to look at the code running. Your application may do something you do not expect while it's actually running. So let's add a little more functionality to this application. We'll create a local function called startProcess. This will be the first function our pbMain function actually calls. So we've created the startProcess function, and this will be the first one called. One approach that you can take in your functions and subroutines is to do some form of logging. So that's what we're going to be doing here. We're going to use an inbuilt ability of PowerBasic to extract the name of the function or subroutine you're currently in using the func name $ command. This will return the name of the function or subroutine that your application is currently in. So that if we try running this application, what it will do is it will push out to our log the name of the function it's currently within, in this case, the startProcess function. This is very useful as it saves you having to hard code the name of function inside the function itself. So we're now going to expand our application further by allowing our startProcess function to call a second process function. So this nested process will be kicked off as soon as startProcess itself begins. And then when second process runs, we're going to actually run a third function called reportErrors, passing it a parameter of error details. So now we have an application that has 3 functions that will occur one after the other. So if we attempt to run the application now, it will push these messages out to our log. While these messages are appearing on screen, they could of course go to a file, tracking the progress of your application as it runs. We're going to add a little more realism to each of these functions by putting in a sleep command which will emulate the process actually doing something. So we'll put 100 milliseconds into startProcess, and we'll put a similar delay into the second process function by adding a sleep command for 200 milliseconds. And in our third and final function, we will also add a similar delay. We'll make this one slightly longer and we'll mark it for 400 milliseconds. In complex applications, it's sometimes useful to know how your application arrived at a particular function. We can determine this quite easily by using the Callstack command. This command takes a single parameter, which is the path and name of a file you wish to write to. When our application runs, it will record into this file each of the functions it passes through as part of the processing. However, for the Callstack command to actually function, we need to make a change to the beginning of our application. At the beginning, we have a command called toolsOff. This turns off all the debug tools, including Callstack. So we will comment this line of code out and we will run our application once more. Now that that has been commented out, it should now create our Callstack file. So if we have a look in our folder, we should see there's a new file which has just appeared called stackframe.txt. If we open that up, it will give us a list of each of the functions our process has gone through: the pbMain, the startProcess function, the second process function, and the reportErrors function. And as you will see, it also gives details of the parameters that have been passed to each of the functions or subroutines. This can be incredibly useful to work out how your application managed to arrive at a particular function when you were not expecting it, especially if the details passed to that function were erroneous. The next command we're going to look at is the profile command. The profile command is another one of our debug processes. You can put this at the very end of your pbMain function, and again it takes a single parameter, which is the name of the file you wish to write to. when our application runs, it will create and add to this file. So if we run the application now, we can see it in process. There's our application now having completed, and if we go back to our folder, we can see there's now a file called profile.txt. If we open this file up, we will see there are 3 columns of information. On the left-hand side is the name of each of the functions that have been called. The middle column is the number of times that function has been called within the run of this session of the application. For example, the funLog function has been called 4 times, whereas the other functions have only been called once. The final column on the right-hand side is the number of milliseconds that function has been running. For example, the funWait function is taking 1424 milliseconds. Each of these functions is accumulative. For example, the startProcess function is taking 714 milliseconds. The startProcess function is still running while the secondProcess function is running. As you will see from the Windows help file for PowerBasic, there's a good deal of information on the profile statement and how to interpret a profile report. This can be ideal for spotting bottlenecks in your application. This should allow you to determine which processes are taking longer than they should to run, or a process that's been run many more times than you expect. So in summary, what we've looked at today are mechanisms by which you can actually look at your application and determine where errors are occurring. Firstly, we looked at compilation errors, where your application will fail to compile. Secondly, we looked at process logs, allowing you to print out information on which function or subroutine is currently running to a process log. Next, we looked at the Callstack command. This command allowed you to print out to a log the name of each of the functions or subroutines with their associated parameters to a log in the order in which they occurred. And finally, we looked at the profile command, which gave you details of how many times each of the functions in your application had been called and how long the program was running that particular function. This is just the beginning of how to debug your applications. But that's it for today. Thank you for watching.